Swayam Prabha. Digital India. Educated India.
We are going to do additions to alkynes. Alkynes are nothing but a double pi. So you have a pi bond in the y direction and a pi bond in the x direction and a bond going through it in the z direction. So you can add to the pi bond in x direction, add to the pi bond in the y direction. You just do everything twice. So as you can see, there is a pi bond in the x direction and a pi bond in the y direction, and you can keep adding to both of these pi, sometimes independently and sometimes simultaneously. So you can add to the y direction pi and the x direction pi. So whatever you do on the alkene, you can do twice as much on the alkyne, double additions. That's what we're going to see on alkynes. All right. Alkynes have an affinity for hydrogen. Alkynes can react with hydrogens, and you can add 2 hydrogens across each of those pi bonds. Are they stereospecific or regiospecific? We are adding 2 hydrogens, so really there's no regiospecificity in that sense across a single triple bond. It can be stereospecific. We can add syn or we can add anti. And both the terminal alkyne and the internal alkyne can do these reactions. So if you take the internal alkyne, it is going to be non-regioselective, and you can have stereospecific additions. And it's the same here. If you take the terminal alkyne, it will be non-regioselective, but it will be stereospecific. Let's look at these reactions. We're going to talk about hydrogenation, adding hydrogens. And we're going to do a non-regioselective and a stereospecific reaction, additions. Let's look at some additions here. Hydrogenation. We are going to look at some non-regioselective stereospecific additions. Let's see how they're going to work out here. We have here palladium, carbon, and hydrogen gas. So you take hydrogen gas and really pump it in at, let's say, like 6 atmospheres. It's going to be very high pressure. And so you need to have these very thick steel vessels, where you can do the job. Now, you could also do other metals like Raney, nickel, and so on. But, palladium, carbon does do the job. Now, the palladium carbon, this is interstitial carbon, so the mechanism's kind of complicated, and I don't want to write it all out thinking, I know it all. There are lots of different pathways, and I'm just going to say that if this, let's say this is your palladium with, carbon, and there'll be layers of it, the hydrogen would come in and get absorbed. So the hydrogen bonds here would break, and they would form bonds to the palladium. It's like grass that grows on the top. Then on top of that, you're going to have the alkyne also get absorbed onto the surface. Then these hydrogens kind of creep in here and form sigma bonds, break that pi bond and form sigma bonds. And so now you're going to get those hydrogens adding to the pi bond, and so you would get a double bond. And since the metal is holding the hydrogens only on one side here, it's going to be a syn addition. This we saw before. Alkenes also add to hydrogens in the presence of heavy metals like palladium, platinum, and so on. And this can happen again. There's always going to be more hydrogens absorbed on this surface, and so those hydrogens are going to add to that pi bond, just like we added hydrogens to alkenes with platinum hydrogen or nickel hydrogen and so on. So it is a syn addition just because you can put those hydrogens only on one side. So therefore it is stereospecific and syn. It's non-regioselective because it's going equally on both sides. It's not going more on one side or more on the other side. So it's going to go equally. So there's no regioselectivity as such, and it is syn. The only bad thing is it's really hard to control this reaction because once you form this, it's going to add again. So you would get this, and then you would get totally hydrogenated to the point that there is no real stereochemical outcome that you can see visibly. It's just going to be like gasoline. So this can be happening in industry, and it's about 100% efficient, really. It's very efficient. And we're going to take a nice alkyne and turn it into gasoline. Not really. We don't, most of the time we won't really want to do that. What we would like is to stop right here. We can get alkynes to go to alkenes. That would be really nice. So here you would add hydrogen against sin, and you would get completely hydrogenated alkynes. And so you would literally take your nice expensive alkyne and turn it into a cheap gasoline. So here's your alkane. And this is really not something we may always want to do unless, there's some specific reaction that needs hydrogenation. Most of the time we'd like to stop here. And that's what these reactions are going to do. So this is a reaction that goes to completion. What about if we don't want it to go all the way? We want to stop right here. Let's look at an example here. This is Lindlar's catalyst. This has got lead acetate, 5% palladium, calcium carbonate. So it's a catalytic amount of palladium that you need, which is really nice because palladium's expensive, you know that, right? So that just needs 5%, and quinoline. And then you don't really need a very high pressure of hydrogen. So once you have this, the reaction goes in a completely different pathway. So I'm not even going to write a mechanism for this. I'm just going to say that if you have that palladium on calcium carbonate, and you have all of these things on it, it's like a poison catalyst. So you got all of these laced on the palladium, and then you would have hydrogens here. These hydrogens can break a pi bond of a triple bond, but they cannot break the pi bond of a double bond. So therefore, the reaction will stop after you add one of these. So here is this molecule coming in, and these hydrogens would add over here to give you a bond where you have both the hydrogens on the same side. The way the catalyst is holding the hydrogens, it's impossible for it to turn around and attack on the top. So it's going to be going right at the bottom. That is a syn addition. And the catalyst has been weakened to the point that I cannot break a pi bond of a alkene. So the reaction stops here. And this is also almost about 100% here. I would say about at least above 90%. So this is a very good way of stopping at a Z alkene. Let's look at what we can do if we don't want a Z and we want an E. Well, obviously we cannot use this because this can only add in one direction. We got to bring something that can add in opposite directions. Let's look at that. Sodium ammonia. We've never seen this before, and the mechanism is also very different. When you say sodium here, this is not your sodium chloride sodium. This is your sodium metal, the thin wire or the chunky sodium that you have. That chunky sodium is going to be dribbled onto this ammonia at very low temperature. You get a nice blue solution, and then you drop the alkyne into there, drop-wise, and it's going to react. How? Well, the sodium is a metallic sodium, so it's still got its S1 electron, so it's got an electron here. It's not a sodium plus, it's a sodium metal. And you got ammonia here. So this is the reactive species. It's going to pump its electron into the pi bond. So let's say it pumps it like this. This is a 1 electron, so I'm going to draw a very weird looking arrow like that. But once you pumps that 1 electron into there, that's too many electrons for this. So these electrons then move over to this carbon. So because it's only half a bond or 1 electron moving, we put this what you call fish hook arrows, which you're going to see later. So don't worry about it for right now. Important thing is this is giving electrons to this carbon, and that's too many electrons to that carbon, so it's pushing that electron to the next carbon. So now this gets pushed over, and you have 1, 2, 3, 4. These are going to be on the bottom of this carbon. You're going to get a pi bond, and these are going to be in an orbital by itself. This is an anion because you can see 1, 2, 3, 4, 5. That would be a negative charge here. This is going to go on the top, so you would have an orbital here that's got 1 electron on the top, and you'd have these ethyl group over here. This is the exact reason why we have anti-addition, because you can see these want to be on opposite sides. They are electron orbitals, which means it's just an electron cloud. An electron cloud here, an electron cloud here is much better on opposite sides than on the same side. If they were on the same side, they were going to be butting heads. So you wouldn't get a situation where they would be on the same side. Well, now that you have this, well, what about this? What's this going to do? Well, there's ammonia. This is an anion. The pKa of an sp2 anion is about 44. This is about 38. So this is going to be more acidic than this, which means this is going to protonate. The ammonia is going to protonate that. And you would get a hydrogen here. And this is still over here. It's going to be a single electron or a radical, a vinyl radical. Those aren't that great. They're not really happy. They're longing for that partner, for that other electron to join them. So again, your sodium does the job. Your sodium goes in and gives that electron over to that orbital. So now you have 2 electrons in that orbital, which is great because once you have 2 electrons, it's going to be an anion, and the anion is going to then deprotonate an ammonia. Again, vinyl anions are quite basic, much more basic than an ammonia, NH. So now that you have your hydrogens on opposite sides, that's perfect because you are going to get an anti-addition giving you an E or a trans alkene. An E, or what you may call a trans alkene. And this is about 86%, which is pretty good considering that you're just throwing in some ammonia and sodium into this alkyne. So we can get syn addition or we can get anti-addition. So this is going to be anti overall. You're doing it stepwise, but it's anti. So this is stereospecific and anti-stereospecific, and this is syn stereospecific. So we can do regioselective stereospecific additions to alkynes. By varying the reagent, we can choose whether we want to do syn addition or anti-addition, which is great. Now, is there absolutely no regioselectivity in this reaction? Let's look at this. Let's say I added sodium amide, and ammonia to this. So here we have a terminal alkyne and an internal alkyne. Which one do you think is going to prefer? We might think that you want to go to the terminal because that's less steric, but that's really not what happens here. What happens here is that you are going to get the internal alkyne being selectively hydrogenated to a trans. And so here, because we have sodium and ammonia, it's going to go trans addition. However, this has been spared. Why is that? Why do you think that is? What happens here is when you have sodium ammonia, you are going to add to this alkyne. You are also going to deprotonate this alkyne, and you are going to get an anion here. Once you have an anion here, it's going to be a lot more reluctant to accept electrons from sodium to create another anion here, because 2 anions here, that's going to create a lot of stress and a lot of repulsion here and strain. So therefore this is going to be spared, whereas this is then going to be under attack. So after your reaction here, where you're going to get a reduction and addition here, anti-addition, anti-hydrogenation. Then you would, during the final workup, you would protonate that and you would get a product here. This is your major product. So yes, if you have terminal versus internal alkyne, you can use this reagent to distinguish between them and reduce the internal to an E and keep the terminal the same. So this is a very rare incident where you can choose between two alkynes. All right, in summary, additions to alkynes can happen on both pi lobes. If you get addition of hydrogens to both lobes, you would get an alkane. However, if you want to stop at your alkene, we can choose whether we want to get a Z alkene or an E alkene. The way to do that is to vary the reagent. If you had Lindlar's catalyst and poison the catalyst, then you would get addition on one side of the double bond, and that would be your major. Whereas if you have sodium ammonia, the way that it adds is going to be keeping those electrons apart, anti, and therefore your addition is going to be an anti-addition. Here's an example of where you can also choose between an internal and a terminal using a specific set of reagents. Now, one of the things that I'd also like to note is if you, let's say, have a terminal alkyne and an internal alkyne and you hydrogenate them, this is your delta H of hydrogenation. Here's something I want to leave you with. If you have a terminal alkyne and an internal alkyne, you can see that even energetically they are not the same. A terminal alkyne, when you hydrogenate it, you're releasing 69.9 kcals per mole, about 70 kcals per mole. When you hydrogenate a internal alkyne, this is 2-butyne and this is 1-butyne. If you hydrogenate an internal alkyne, you're only releasing 65.1 kcals per mole. That means to start with, this had a lower energy. So it is lower in energy than your terminal alkyne by 4.8 kcals per mole, delta H. And so that is quite high. So that means this is more stable than this by about 4.8 kcals per mole. That means this is more stable. And why is it more stable? Mainly because you have two R groups donating to that pi bond. That pi bond is more nucleophilic, and therefore it's also going to be more reactive. So that's another thing that we would like to point out here. Internal alkynes are going to be more nucleophilic and more reactive. And the fact that they are more nucleophilic means they will react faster or more with electrophiles. So the reactivity would also be more for internal than terminal. So those are some of the main differences between internal and terminal alkynes. All right, guys, we will see you with more additions. Talk to you soon. If you have any questions, don't hesitate to ask me. Bye.